The theme for part 4 is to create functions that have characteristics that we would like it to have. And we've seen this before with linear functions, and that's reviewed in this part of the practice problems as well. But we also now are able to work with quadratic functions and polynomial functions. So, for example, polynomial function has particular zeros. Remember, the zeros are really just the x values of the x-intercepts. In other words, they're the numbers that you can plug in for x that make the y-coordinate equal to 0. So we just call those zeros of a polynomial or of a function for short. So we know that if a function has these factors, then when you plug 0 in for x, the output will be 0. When you plug 2 in for x, the output will be 0. When you plug negative 2 in for x, the output will be 0. So a function that looks like this will have zeros at x equals 0, x equals 2, and x equals negative 2. But this polynomial will not be a degree 5 polynomial. We can see that this only has 3 terms, and so the biggest power of x here is x to the first, x to the first, x to the first. So multiplying that out would give us an x cubed as our highest power of x, which means the degree of the polynomial would be 3 and not 5. But we know that we can increase the multiplicities of these things without changing where the zeros are. So for example, I could make this multiplicity 2 and this multiplicity 2, for example. Now I have my highest degree. I'll have an x squared term here, I have an x squared term here, and I have an x term here. So the total degree of this polynomial now is 5, and the zeros are still 0, 2, and negative 2. So this is one where there's, notice it says some of them have more than one answer. There are several correct answers to this. As long as the total degree is 5 and you have these 3 factors, then that will work. And second problem, I want my polynomial to have, I have 3 particular zeros, and I want it to be degree 3, and so that's going to sort of dictate what this looks like. So it could look like that, and that will have the correct zeros. I can tell that plugging in 1, negative 3, or 2 for x is going to make this equal to 0. But there could also be a number out here, and that was true here too. I could have made, in number 1, I could have made this 3 times x squared times x minus 2 squared times x plus 2, and that still would be fine. So you can have a number out here to scale it, and that doesn't have any effect on where the zeros are. So this does have these 3 zeros. This does have the correct degree, but I don't know what the y-intercept is going to be. So by putting an a here for a scaling factor, by putting this out in front, I can figure out what the scaling factor has to be in order to accomplish that goal. And we saw this before with some of our fitting of quadratics. So the way we did that was we said, well, according to the form that I have, plugging 0 in for x is going to give me a times negative 1 times 3 times negative 2, which is 6a. According to this fact, I want f of 0 to be 2. So if I know that f of 0 is 6a, and I wish that f of 0 is equal to 2, combining those two things together tells me that a should be 1/3. And so the answer is that f of x should be 1/3 of x minus 1 times x plus 3 times x minus 2. That has the correct degree, the correct zeros, and satisfies the property that f of 0 is equal to 2. In number 3 and 4, we're reviewing linear functions. This is the same kind of questions you saw in the last unit. Remember that if I know 2 points, then I know the equation of a line. And so in this case, I can just find the equation of a line that goes through these two things. The slope, if I do a rise over run here, the slope is going to be positive 2. And so I can say y minus 4 is equal to positive 2 times x minus 0. That's point slope form using that point and a slope of 2, and so I can rewrite that y equals 2x plus 4. And if I want to write that in function notation, the way it asks me to, I should say f of x is equal to 2x plus 4. This is eminently checkable because none of the numbers given here are hard. It's very easy to check that f of 0 really is 4 and f of negative 0, which is what's supposed to happen in order for the function to go through those 2 points. In number 4, we're given the y-intercept, but we're not told anything else. We're not told a second point, but we are told that the graph is perpendicular to a given line. And so because I know how to write this in slope-intercept form, so this line, if I solve for y, is the same thing as y is negative a half x plus 3. This line has slope negative 1/2, and so the linear function that I want here should have slope equal to 2. Remember that the relationship between the slopes of perpendicular lines is that their slopes should be negative reciprocals of each other. And so the line that has a slope of 2 and a y-intercept of 3 is going to look like that. So that has the correct slope and goes through the point 0, 3. Easy to check that f of 0 equals 3. In the last 2 problems, we have some description of quadratic functions. In the first one, we're just told what the x-intercepts are, but remember this is the same thing as being told what the zeros are for a polynomial. It's really no different. You're telling me the x's that make the y-coordinate equal to 0. And so just like I did for the polynomials, I can start off by saying that x minus 1 and x plus 2 should be factors of this polynomial. And if you check, when you plug 1 in for x, you'll get 0. When you plug negative 2 in for x, you'll get 0. And there can be any number out here at all that you want. Put a 5 out there or a negative a half or whatever, and that'll also be okay. So this is another one where there's lots of answers because there are lots of polynomials that go through those 2 points. In order for it to determine a polynomial uniquely, I would have to be given some third piece of information, and that's basically what happens in number 6. So in number 6, I'm told where the vertex is, and we learned that there's a particular form that quadratics can have that emphasize the role of their vertex. So so-called vertex form highlights the role of the vertex. And we talked about the fact that any quadratic function that has this form is going to have its vertex at 1, negative 2. X equals 1 is what makes the squared part here 0, and then minus 2 is going to tell me the y-coordinate. So when I plug 1 in for x, I'm going to get 0 squared minus 2, which is negative 2. So that form highlights the role of the vertex, but the a could be anything. This could be negative a half or 5 or whatever, and it won't change the fact that the vertex of this parabola is at the point 1, negative 2. So in order to know what a is, I have to know another piece of information. So we saw up here that we weren't given any other piece of information, and so we could make that number be whatever we wanted to. So we can make that be 5 or 3 or negative 1/2 or just 1, just ignore it altogether. So there's lots of things you could make it there because there was no other piece of information given. In this case, I'm told the y-intercept is 0, 1, and so that means that I'm told that g of 0 should equal 1. That's what that fact means. Because of the form that I know g of x has to take, I know that g of 0 is a times negative 1 squared minus 2. In other words, I also can plug 0 in for x in the formula that I have. And so I know 2 different things about g of 0. G of 0 should be 1, and g of 0 should be a minus 2. So for both of those things to be true, we would have to have a equal to 3. So my answer is that g of x is 3 times x minus 1 squared minus 2. If you check, that will have the right y-intercept, and because of its form, it has the correct vertex. But again, the way I'm finding that out is by starting off with a generic form and then plugging 0 in to get one fact about g of 0, and taking the given information to give me a second fact about g of 0. And the fact that those are both things about g of 0 means those have to be equal. So I know that 1 has to be the same thing as a minus 2, and from there I can figure out what a is.